Hello everyone, welcome to MACM 101 Tutorial 4. In this tutorial, we'll continue our discussion on predicates and quantifiers. So let's get started. Our first question says, determine which of the following arguments are valid and which are invalid. Provide an explanation for each answer. And the universe consists of all people who are presently residing in Canada. So the first part, it says all mail carriers carry a can of mace. Mrs. Bacon is a mail carrier. Therefore, Mrs. Bacon carries a can of mace. So we can start this question by assuming P of X be a mail carrier. So let P of X is a mail carrier and Q of X means carries a can of mace. Now, the first statement, it can be interpreted as for all of x, P of x implies Q of x. And now the second statement, which says Mrs. Bacon is a mail carrier, since we are talking about a specific person, we can say P of A. And now we have P of x implies Q of x. So using the rule of universal specification, which says if an argument is true for all replacements by members of the universe, then that open statement is true for each specific individual in that universe. Meaning if P for all x P of x is true, P of A is true for each A. So here I can say P of A implies Q of A. And I had P of A. Now using modus ponens, you can safely say the answer is Q of A, meaning Mrs. Bacon carries a can of mace. So we can write the rules. P of A implies Q of A is using rule of universal specification. And our conclusion is drawn through modus ponens. So for the second part, it says all law-abiding citizens pay their taxes. Mr. Pelosi pays his taxes. Therefore, Mr. Pelosi is a law-abiding citizen. So here let P of X be a law-abiding citizen and Q of X be pays their taxes. So from the first statement, all law-abiding citizens pays their taxes. I can write it as for all x, P of x implies Q of x. And in the second part, since we are talking just about Mr. Pelosi, I can write it as Q of A. So from this, using rule of universal specification, we can say P of A implies Q of A. And from the second part, we have Q of A. Now, this does not bring us to any conclusion because there's no rule or law which uses these two premises to arrive at any specific conclusion. But if we were to take the converse of this, it would be for all x, Q of x implies P of x. It's just the reverse of what we had. Now it can be specified as Q of A implies P of A, and we had Q of A. So using modus ponens, I can arrive at the conclusion P of A. But since the converse of the statement is true, the actual statement is false. And that's our answer. So moving on to the third part, it states all people who are concerned about the environment recycle their plastic containers. Margaret is not concerned about the environment, therefore, Margaret does not recycle her plastic containers. So, from the first statement, I can write P of X means people concerned about the environment. Q of X would be recycles their plastic containers. So my first part, it would give me for all x, P of x implies Q of x. And the second statement, which is Margaret is not concerned about the environment, it gives me not of P of x. Sorry, it's P of A. Again, using rule of universal specification, I can rewrite the first statement as P of A implies Q of A, and the second statement would be not of P of A. So there's no rule or law which brings me to any conclusion related to this. So let's take a look at the inverse of this. So the inverse would be not of P of A implies not of Q of A. And we have not of P of A. So using modus ponens again, we can arrive at the conclusion not Q of A. So using the inverse, we are able to arrive at the conclusion which was asked in the question, that Margaret does not recycle her plastic containers. But since we were able to say using the inverse, we can say that the question itself is false. Now moving on to the next question, it says for a prescribed universe and any open statements Px and Qx, prove that for all x, Px and Qx is logically equivalent to for all x, Px and for all x, Qx. Now to solve this kind of question, what we can do is use a two-step approach. So using the left hand side, you assume that the left hand side is true and arrive at the right hand side. And in the second step, you assume the right hand side to be true and arrive at the left hand side. So if you are able to get the conclusion in both the steps, your answer is true. So let's start with the first step. So my first step would be if for all x, Px and Qx is true, then for all x, Px and for all x, Qx is true. So this is the statement which we are trying to prove. And now moving over to the proof. So we'll start by assuming that the left hand side is true. So suppose for all x, Px and Qx is true. Now, if there's a variable a which is in the domain, and so if it's in the domain, we can say that P of A and Q of A is true. So now if P of A and Q of A is true together, we can safely say that P of A is true and Q of A is true. So this is just using the definition of and. We know if two variables A and B are true, then they will be separately, they'll be true as well. So now once we have this, so in the domain, if P of A is true, that means I can generalize it saying for all x, P of x is true. Because A is any arbitrary variable in the whole domain. So if P of A is true for all A's, it's safe to say that for all x, P of x is true. And similarly, you can also write for all x, Q of x is true. Now, since they both are true separately, they will be true when we join them together. So it means for all x, Px and for all x, Qx is true. So this was our first part. Moving from left hand side, we arrived at the conclusion on the right hand side. And now looking at the step 2. Now our assumption is if for all x, Px and for all x, Qx is true, then for all x, Px and Qx is true. So moving on to the proof of it. Now here we will suppose that the right hand side is true. So suppose that for all x, Px and for all x, Qx is true. Now this would mean that for all x, Px is true and for all x, Qx will be true separately. So now if A is in the domain and they are true separately, I can say P of A is true and Q of A is true. So now again, if they are true individually, we can use a conjunction and say that P of A and Q of A is true. So now here, if A is an arbitrary variable in the universe, we can generalize it by saying for all x, Px and Qx is true. So now we were able to start at the left hand side and arrive at the right hand side in step 1. And in step 2, we were able to start at the right hand side and arrive at the left hand side. So this concludes that both of the statements are logically equivalent. Now moving on to question number 3. It says provide the reasons for steps verifying the following argument. Here A denotes a specific but arbitrary chosen variable from the given universe. And our premises are for all x, Px implies Qx and Rx. And the other premise is for all x, Px and S of x. And the conclusion which we want is for all x, Rx and S of x. The step 1 is clearly a premise, and so is our step 2. In step 3, it's quite similar to step 1 because here we are using the rule of universal specification on step 1 to replace the x with an arbitrary variable a. In the fourth, it should be p of a instead of p of x. So it's similar to step 3. Again, we are using rule of universal specification on the other premise. And now since we have p of a and s of a, I can write p of a, which is using rule of simplification on step 4. And now using step 3 and step 5, I can use modus ponens and arrive at q of a and r of a. Because in the step 3, it's p of a implies something, and in step 5, I have p of a. So my conclusion would be that right hand side in step 3. Now, again, using simplification on step 6, I can write r of a. Now, for the 8th step, again, it is coming from step 4. We had p of a and s of a, so that means they both are true. So using simplification on step 4, once again, we get s of a. Now, since we have r of a and s of a separately, I can use the rule of conjunction to join them together and say that they both are true together. Now, since this is true for an arbitrary variable, so this is true for all a's. So if it is true for all a's, I can use the rule of generalization to come to the conclusion for all x, rx, and s of x. And that's our answer. So the given argument is valid. Now moving on to fourth question, it says give a direct proof that for all integers k and l, if k, l are both even, then k plus l is even. So one thing I want to say here is that if you are to prove something, you need to give a general proof. It cannot be proved using an example. I cannot say 2 plus 4 equals 6 and that's my answer. That's why it's even. So if you need to disapprove something, then giving an example is fine, because all you need is one such case where uh, where whatever you have assumed or whatever is given is false. But in the case of a proof, you will have to give a generic definition or a generic answer in terms of variables alone. So in this, let's start by supposing k and l are even. So we can write k as 2a and l as 2b, which will be for some integers a and b. Now this comes from the definition 2.8 in your book, which states that n is even if it is divisible by 2. Therefore, or otherwise, we can say that there exists an integer r so that n equals 2r. So once we have this, we can write that the sum k plus l, it's equal to 2a plus 2b, and it's equal to 2 times a plus b. So if you want to write the rule used here, it will be using distributive law of multiplication over addition of integers. So by using the same definition 2.8, we can write, since a plus b is an integer and k plus l is equals 2 times c plus d, that means 2 times some integer, so k plus l is even. And that's the proof. So moving to the last question of this tutorial, we have give a proof by contraposition that for all k and l, if kl is odd, then kl are both odd. So one thing to note here is that in the fourth question it was give direct proof, while here it's proof by contraposition. So by contraposition, it would mean that we would assume the reverse of whatever's given in the question and try to arrive at the conclusion. So here will the contrapositive statement would be for all integers k and l, if k and l are not both odd, then kl is not odd. We can also say that if at least one of k, l is even, then kl is even. So that means we don't worry about what the other variable is. So if even one of these variables is not odd, that means if it's even, the answer k times l will come out to be even. So this would be the statement which we'll try to prove. So for the proof, let us assume that k is even. So using the same definition 2.8, we can write k equals 2a for some integer a, and then k times l can be rewritten as 2a times l, and which is also equivalent to 2 times al. This is using associative law of multiplication for integers. Now, since a was an integer and l was an integer, al is also an integer. So consequently, by again using the definition 2.8, I can say KL is even. Now, one thing to note here is that the result did not require anything about the integer L. So whether L is even or not, it does not matter. If just one variable K is odd, even, the answer would come out to be even. So that was the proof. And this concludes our tutorial. Thank you. See you next week.